Welcome back to Talk Tensors, everyone. Today we're diving deep into, well, something a little bit different.
Different, yes, but foundational.
I like that.
And I think it's gonna, really get you thinking about what it even means for a program to know something.
Definitely not our usual deep learning models, that's for sure.
Right. We're taking a step back from, the algorithms and the training data and all that. We're going right to the logical heart of things.
We're tackling this paper on the logical content of logic programs.
By Alexander Garigew.
Exactly.
And just to set the stage, I think a lot of folks, when they hear logic programming, they might picture, Prolog, maybe some dusty AI textbooks from back in the day.
Yeah, definitely not the hot new transformer model everyone's buzzing about.
But here's the thing. This paper is about something much deeper than any specific language or implementation. It's about understanding what knowledge is in the context of a program, any program that uses logic as its core.
Okay, I'm intrigued. But knowledge, that's a pretty loaded term.
It is. And that's why this paper is so fascinating. It introduces this idea of a support relation, like a way to formally express what a logic program backs, what it stands behind.
So not just what it can compute, but what it intrinsically, asserts as true.
You got it. It's denoted by this symbol, AP. So you read that as program P supports the statement.
And this support, it's not just some fuzzy idea, right? It's tied to specific logical systems.
Right, and that's another really cool part. Depending on how we interpret things like or and not within the logic programming framework, this support relation can line up with, say, classical logic.
Like good old true or false, the kind we all learned in school.
Exactly. Or it could map to intuitionistic logic, which is, a bit more nuanced in how it handles truth and proof.
So depending on the choices we make when defining the program's logic, the knowledge it represents takes on different flavors.
Precisely. It's like we're uncovering these hidden connections between the very structure of a logic program and these fundamental systems of reasoning.
Okay, that's pretty mind-blowing. So how does the paper actually formalize all of this?
Well, they use what's called base extension semantics within this broader idea of proof-theoretic semantics. Now, proof-theoretic semantics, it's a bit different from how we usually think about meaning in logic.
Because usually we talk about models, right? Like, is this statement true in this particular scenario?
Exactly. But proof-theoretic semantics, it flips the script. It says, look, meaning comes from the proofs, the demonstrations themselves.
So it's not about finding a model where the statement holds. It's about being able to construct a valid proof.
Precisely. And the base extension semantics, it adds another layer. It says, let's think about a program's knowledge as this base, and then explore how that knowledge could potentially grow.
Like what new conclusions could we draw if we added new information or rules to the program?
Exactly. So we're not just looking at what the program currently knows, but what it could come to know.
So let's tie this back to our bread and butter, machine learning. Why should folks who are deep in neural networks care about any of this?
Great question. And I think there are a few key reasons. First, knowledge representation. We're always trying to find better ways for our AI systems to understand and work with knowledge, right?
Sure, whether it's a chatbot, a self-driving car, or, some kind of future superintelligence.
Exactly. And logic programming with its clear declarative style has always been appealing for representing knowledge.
Because you can explicitly state the rules, the relationships, and then let the system reason.
Right. So this paper, by giving us a deeper understanding of the logical content of those programs, it gives us more tools to work with. It helps us think about the limits, the guarantees, all the things we need when building reliable AI.
Makes sense. And what about the more theoretical side?
Well, this whole connection to proof-theoretic semantics, it opens up some very interesting avenues.
Like what?
For one, it links logic programming to a whole body of research in proof theory, a field that's been around for, quite a while and has tons of rich results.
So we can potentially borrow techniques, ideas from that field and apply them to problems in AI.
Exactly. And on the flip side, maybe this perspective on logic programming can even lead to new insights in proof theory itself. It's a two-way street.
A virtuous cycle of knowledge, I like it.
And this focus on the support relation, on what a program intrinsically affirms, it's also just a really elegant way to think about correctness, about ensuring our programs are doing what we intend them to do.
Right, because if we can clearly define what a program knows, Then we can verify if that knowledge is consistent, if it leads to the right conclusions.
Absolutely. And in areas like, say, formal verification, where we're trying to mathematically prove the correctness of software, well, this kind of approach could be super valuable.
Okay, so we've laid out the big picture. Let's get our hands dirty and dive into some of the specifics. Now, I have to admit, when I was skimming the paper, I stumbled a bit on the notation. All those symbols, it can get a bit intimidating.
Oh, absolutely. Formal logic, it has a language of its own. But don't worry, we'll unpack it together.
So the paper starts by talking about how to express knowledge within this framework. And the first concept they introduce is, well, implication.
Right, the good old if this, then that. And they say that program P supports the implication. AP means essentially if P were to support Hef, then it would also have to support he.
Okay, so it's like this hypothetical thing. We're saying if we assume it's true in the context of P, then P would also have to be true.
Exactly. And they generalize this with this notation, OAP.
Which looks even more scary.
But it's not too bad, really. Think of OEW as like a set of formulas, maybe some additional information or assumptions we're adding to our program P. So this whole thing says if P were extended to support everything in A, then it would also have to support P.
Okay, so it's still about this hypothetical extension of the program's knowledge.
Precisely. And they formalize this by saying for any program Q that includes P, so Q is like an expanded version of P, if Q supports every single formula AP, then Q must also support.
So we're talking about all possible expansions of the program's knowledge, not just the current state.
Exactly. And this whole idea, it's at the heart of base extension semantics. We're exploring what the program could potentially know, not just what it explicitly states.
Makes sense. Now, where things started to get really interesting for me was when they got to disjunction.
Ah, yes, the or. And this is where the paper really digs into the subtleties of knowledge representation.
Because on the surface, you might think, okay, program P supports or PIS. That just means it supports either one of them.
Right, like either S is true or cis is true. That's the standard interpretation.
But the paper argues that this is actually too strong a requirement when we're talking about knowledge.
Because we can know that one of two things is true without necessarily knowing which one specifically.
And they illustrate this with the classic lottery paradox.
A great example. So imagine a lottery with 1,000 tickets. We know for a fact that someone will win.
Right, because there has to be a winner.
So in a sense, we could say ticket 1 wins OR, ticket 2 wins OR, all the way to ticket 1,000 wins. That whole disjunction is definitely true.
But we don't know which specific ticket will win.
Exactly. So we can't say our program definitively supports, say, ticket 1 wins on its own.
Even though we know one of those tickets has to be the winner.
Precisely. And to capture this kind of knowledge, they introduce this idea of an implicit disjunction denoted by O.
So it's like a weaker form of or.
Right. And they define it like this. Program P supports set P if and only if for any extended program Q and for any atom A, if assuming 2 in Q leads to A being provable. A and D, assuming N and Q also leads to A being provable, then A itself must be provable in Q.
Okay, that's a mouthful. Can we break that down?
Sure. Think of A as some consequence that logically follows from our statements. So we're saying if either CO or O, when added to our program, would each individually lead to A being true,
then A must also be true if we just know that Q is true.
Exactly, because essentially we're capturing this idea that one of those alternatives must hold, even if we don't know which one.
So going back to our lottery example, if knowing ticket 1 wins would lead to some conclusion, and knowing ticket 2 wins would also lead to that same conclusion,
then knowing ticket 1 wins, ticket 2 wins would also guarantee that conclusion, even though we don't know which ticket is the actual winner.
Makes sense. So the implicit disjunction, it lets us represent this kind of knowing that one of the possibilities is true without knowing which one.
Exactly. And they make the point that the standard explicit disjunction, the AE, it makes a stronger claim.
So it doesn't necessarily mean that is true or kibis is true in the usual sense?
Right. It just means that any consequence that logically follows from either one of them individually also follows from the disjunction as a whole.
Okay, that's subtle but important. Now, what about negation? How do they handle that?
Well, they start with the familiar idea of negation as failure, or NAF for short.
Which, if I recall, is like saying, if we can't prove something, then we assume its negation is true.
Precisely. So program P supports if and only if we can't prove from P.
And this makes sense in the context of logic programming, right? Because the system is trying to find a proof, and if it fails, well, that's our way of saying, okay, looks like the negation is true.
Right. And this NAF, when combined with the standard disjunction, it preserves what's called the disjunctive syllogism.
Which is
Basically, it says, if you know A or B and you know not A, then you can conclude B.
okay, that's pretty intuitive.
It is. But the paper, they're interested in finding a kind of negation that works well with their implicit disjunction.
Because they want to keep that disjunctive syllogism property even when we're dealing with this weaker form of or.
Exactly. And to do this, they introduce this special element. They call it wu.
Bottom.
Yeah, it represents like a contradiction, a state where everything is true.
Okay, sounds a bit paradoxical.
It is, kind of, but they use it to define their new negation. And they define it as simply wu.
So the negation of
Yeah.
is just the implication from oo to this everything is true state.
Exactly. And this might seem a bit roundabout, but it turns out to be a really clever way to define a negation that plays nicely with their implicit disjunction.
And they proved that this new negation does indeed preserve the disjunctive syllogism, even when we're using error instead of the standard error.
Precisely. So they've created this whole coherent system where the implicit disjunction and this new negation work together in a way that, well, makes sense logically.
Okay, so we've talked about implication, disjunction, negation. What's next?
Well, now we get to the heart of base extension semantics itself. And the paper, they lay out all the rules, the support conditions for these connectives in what they call figure 1.
Like a cheat sheet for understanding how knowledge is expressed in this framework.
Exactly. And they also introduce something called an implicit conjunction, denoted by...
So like an implicit and to go along with their implicit or?
Precisely. And it's defined in a way that's analogous to the implicit disjunction.
So if assuming Cole leads to some consequence, and assuming leads to that same consequence, then knowing Cole also guarantees that consequence.
Exactly. But here's a really interesting finding. They prove, in what they call Proposition 1, that this implicit conjunction actually coincides with the standard conjunction, the if.
So while we have these two different ways of thinking about or, the way we combine things with and is actually the same.
Precisely. Which I think highlights that there's something really fundamental about this implicit disjunction, the way it captures this weaker form of knowledge.
Okay, I'm following so far. What else do they cover in this base extension semantics part?
Well, they have this other key result, Proposition 2, which says that program P supports if and only if for any extended program Q and any atom A, if assuming in Q leads to A being provable, then A itself must be provable in Q.
So it's like saying, if being true in any possible extension of the program guarantees some consequence, then itself must already be enough to guarantee that consequence.
Exactly. And the proof is a bit technical, but it cleverly uses a tautology, like a statement that's always true, to establish this connection.
Okay, I'll trust you on the details there. But the main takeaway is that this proposition further solidifies the idea that we're exploring all possible extensions of the program's knowledge.
Right. We're not just looking at the current state, but we're thinking about all the potential ways the program's knowledge could grow.
And how those potential expansions constrain what the program must already know.
Precisely.
Yeah.
And all of this, it's setting the stage for the really mind-blowing part of the paper, where they connect this whole framework to specific logical systems.
Okay, this is where I really started to see the bigger picture. So they asked this question. What kind of logic actually emerges from all of this?
Right. Like if we take this base extension semantics and this notion of support, what are the rules of the game? What kind of reasoning does it allow?
And to make things concrete, they focus on propositional hereditary Harrop formulas.
Which, just to clarify, are a specific kind of logical formula that's often used in logic programming. And as a special case, they also look at horn clauses, which are even simpler.
So they're deliberately narrowing their focus to make the analysis more manageable.
Exactly. They're not trying to handle every possible kind of logic program out there. They're picking a specific, well-studied class of formulas.
And they define these formulas very precisely, using a syntax with D clauses and G clauses.
Which, again, it can look a bit intimidating, but it's just their way of being super clear about what kind of programs they're dealing with.
Right. It's all about being rigorous and avoiding ambiguity.
Absolutely. And they also introduced this unpacking function to deal with collections of clauses.
Like a way to break down these complex formulas into their constituent parts.
Exactly. And then they define what it means for something to be derivable from a program.
So given a program and a statement, can we actually prove that statement using the rules of the program?
Precisely. And they give a step-by-step definition for this derivability, which they denote by EMA.
Okay, so they've defined the kind of programs they're looking at. They've defined what it means to prove something within those programs.
Right. And now they make this distinction between first-level programs and higher-level programs.
Which basically refers to how complex the nesting of implications is within the formulas, right?
Exactly. First-level programs are simpler. They correspond to the well-known horn clause logic. Higher-level programs are more expressive. They deal with the more general hereditary Harop logic.
Okay, so we have our players on the field. We have the rules of the game. What happens next?
Well, now comes the really exciting part. They start proving theorems, linking this whole framework to specific logical systems.
And the first result, Theorem 7, it shows that for these first-level programs, their defined support relation, denoted by A1, corresponds exactly to Stafford's logic.
Which includes standard implication, bottom, conjunction, and explicit disjunction. So all the usual suspects are there.
Okay, so for these simpler programs, the way they've defined knowledge and support, it aligns perfectly with this well-established logical system.
Exactly. But then Theorem 8, it throws a curveball. It says that A1 also corresponds to classical logic.
Like the logic we all learned in school, with true and false and all that.
Precisely. But here's the catch. It only works if we use their defined implication, bottom conjunction, and the implicit disjunction.
So the way they handle, or implicitly, it's what makes the connection to classical logic work.
Exactly. And this is a really surprising result because it means that this weaker, more nuanced way of handling disjunction is actually deeply connected to this fundamental logical system.
Wow, okay. I'm starting to see why you said this paper gets you thinking differently about knowledge.
And it gets even wilder when we move to the higher level programs. Theorem 9 shows that EN2, the support relation for these more complex programs, corresponds to generalized inquisitive logic.
Inquisitive logic, I have to admit, that's a new one for me.
It's a relatively recent development in logic, but it's been gaining traction, especially in areas like philosophy of language and formal semantics.
Okay, so it's a serious thing, not just some obscure theory.
Right. And then Theorem 10, it shows that EN2 also aligns with intuitionistic logic.
Which is another one of those logics that's, well, known for being a bit different.
It is. And again, the key is that it works when we use their defined implication, bottom conjunction, and the implicit disjunction.
So the same pattern emerges. The implicit disjunction, it's what ties these programs to these well-known logical systems.
Exactly. And this is really mind-blowing because it means that this seemingly subtle choice, how we handle or implicitly, has these profound implications for the underlying logic.
So it's not just a technicality. It's a fundamental shift in how we think about the knowledge represented by these programs.
Precisely. And the paper, they even point out that this unexpected result has sparked further research in the field of proof-theoretic semantics.
Because people are trying to understand the deeper connections, right?
Exactly. And I think that's one of the coolest things about this paper. It doesn't just solve a problem, it opens up a whole new way of thinking.
So to recap, we have this new perspective on logic programming, this focus on what a program knows rather than just how it runs.
Right. And this new perspective, it reveals these deep connections to proof theory, to different logical systems.
And it hinges on this crucial idea of the implicit disjunction, which turns out to be much more significant than we might initially think.
Exactly. And all of this, it has the potential to really change how we design and reason about AI systems, especially in areas like knowledge representation and formal verification.
Absolutely. And to give our listeners some context, let's talk a bit about the history of all of this. How did we get here?
Well, the paper rightly acknowledges the foundational work of Koalski, who really laid the groundwork for logic programming.
With his work on horn clauses and their connection to first-order logic.
Exactly. And then, of course, Prolog emerged as this practical programming language that embodies these principles.
So that's the operational side, the how to make it work part.
Right. But this paper, it takes a different route. It dives into the semantics, the meaning of logic programs.
And it does this through the lens of proof-theoretic semantics, which, as we discussed earlier, is all about understanding meaning through the ability to construct proofs.
Precisely. And proof-theoretic semantics, it has a rich history of its own, with deep philosophical roots.
Going all the way back to philosophers like Poetz and Dummett.
Exactly. And over the years, it's had a growing influence on the field of computational logic, with researchers like the author himself contributing to its development.
So it's a serious, well-established field with its own set of tools and techniques.
Right. And within this broader landscape, this paper specifically focuses on what's called base extension semantics, or BES.
And what's interesting is that They don't present BES as just some arbitrary framework they're imposing on logic programming.
Right. They make a compelling argument that it actually arises naturally from a careful analysis of logic programming itself.
So it's like BES was already hidden within the structure of logic programs, waiting to be discovered.
Exactly. And this is a crucial insight because it means that we can view logic programming as inherently about reasoning about knowledge.
Because the base in BES, it can be seen as representing the program's initial knowledge, its beliefs about the world.
Right. And then the extension part, it's about exploring how that knowledge could potentially grow, what new conclusions could be drawn.
So the program becomes like an agent with its own internal knowledge base that it can reason with.
Precisely. And this perspective, it helps to bridge this gap that sometimes exists between the declarative view of logic programs,
where we see them as just sets of logical statements,
and the procedural view, where we focus on how they execute step by step.
So it unifies these two perspectives, showing that they're actually two sides of the same coin.
Exactly. And the paper argues that this focus on the logical content, it's crucial for a number of reasons. For one, it helps us ensure the correctness of logic programs.
Because we can clearly define what a program knows, then we can check if that knowledge is consistent, if it leads to the right conclusions.
Precisely. And it also clarifies the relationship between the declarative and procedural aspects, showing how they're interconnected.
And it helps us understand what inferences can be validly drawn from a program, what conclusions we can actually trust.
Right. And it also gives us a deeper understanding of the expressive power and limitations of different logic programming frameworks.
So we can choose the right tool for the job, knowing its strengths and weaknesses.
Exactly. And the authors, they also briefly mention related work on hereditary Harp formulas, placing their contribution within this broader research context.
So they're not working in isolation. They're building on a solid foundation of previous research.
Right. And I think that's one of the things that makes this paper so compelling. It's not just a brilliant flash of insight. It's a carefully crafted piece of scholarship that pushes the boundaries of our understanding.
Okay, so we've covered a lot of ground.
Yeah.
But I always like to end our deep dives with a bit of speculation, some food for thought.
Ah, yes, our novel notions segment. Always a fun one.
So building on this idea of a program's inherent knowledge, what are some exciting new research directions this work could inspire?
Well, here's a thought that popped into my head while reading the paper. They primarily focus on a static view of knowledge.
Like what the program knows at a given point in time.
Exactly. But what if we considered the dynamic evolution of this knowledge?
Like how a program's beliefs change as it interacts with the world, as it learns new things.
Precisely. Could we extend base extension semantics to model this kind of dynamic knowledge?
Imagine a program that's constantly updating its knowledge base, revising its beliefs based on new information.
Right. And we could use some kind of temporal logic within the BES framework to formally track these changes.
So you can see how the support relation evolves over time, how the program's understanding of the world shifts and grows.
Exactly. And this could have huge implications for AI, especially in areas like machine learning, where models are constantly learning and adapting.
It's like giving our AI systems a formal epistemology, a way to track the lineage and justification of their knowledge.
I love that idea. A real knowledge archaeology for AI.
And here's another thought, building on the paper's brief mention of substructural logics.
Like linear logic and bunched implications. Now, those are some really interesting systems.
Because they're all about resource sensitivity, right? The idea that using a piece of information can actually consume it.
Exactly. And what if we applied this idea to base extension semantics?
So we could have a kind of resource-aware logic programming where drawing a conclusion actually depletes some resource.
And this could lead to entirely new paradigms of programming, where we have to carefully manage the logical resources available to the program.
And this could be particularly useful in areas like distributed computing, where resources are inherently limited.
Or even in modeling complex systems like biological processes, where the availability of certain molecules or energy can dramatically affect the system's behavior.
So we're taking inspiration from these seemingly abstract logical systems and applying them to real-world problems.
Exactly. And I think that's the beauty of this paper. It opens up these unexpected connections, these new ways of thinking about computation and knowledge.
It's a real deep dive, and it leaves us with even more questions than we started with.
But that's the best kind of research, isn't it? The kind that keeps us curious, keeps us exploring.
Absolutely. And I encourage all of our listeners to check out the full paper, the links in the description.
It's a challenging read, but it's well worth the effort.
And on that note, a final thought for everyone to ponder. If we embrace this idea of programs as possessing an inherent knowledge, how might that fundamentally change how we design and verify the intelligent systems of the future? It's a question that will keep me thinking for a long time. Thanks for joining us on Talk Tensors.